when maybe you or somebody else creates an AGI system and you get to ask her one question. What would that question be?
What's outside the simulation?
We're living in a computer simulation. The Matrix is real. Our entire universe is just code running on some alien supercomputer. If you've spent any time on the internet in the last decade, you've heard this claim 1,000 times. Elon Musk says the odds we're in base reality are billions to 1. Philosophers like Nick Bostrom have made mathematical arguments for why we're probably simulated. Even respected physicists are taking this idea seriously. Here's the problem. They're all wrong. Spectacularly, embarrassingly wrong. And I can prove it using nothing but basic physics, information theory, and mathematical logic that anyone with a high school education can understand. Today, we are going to euthanize the most popular myth of the internet age. I am going to show you why the universe isn't a server, it is a symphony. Now, I know the psychology here. I know I'm attacking a sacred cow. For the diehards, this feels like I'm forcing you to take the blue pill. I can already feel the comment section heating up. The Matrix fans are going to crucify me in the comments. The Elon Musk disciples are going to tell me I don't understand advanced physics. And somewhere, a philosophy student is already warming up to type a very angry essay about why I'm destroying people's hope. And I get it. The simulation is a comforting lie. It explains the chaos. It makes sense of the suffering. It's a fun story. But there is a difference between a fun story and the truth. So put down the keyboard, suspend your disbelief for just 12 minutes. Don't judge the verdict until you see the evidence. When we'll apply the hard mathematics, information theory, thermodynamic limits, and the computational complexity of quantum systems, the hypothesis doesn't just weaken, it collapses under its own assumptions. Over the next 12 minutes, we are going to do what the popular versions of this argument almost never bother to do: run the numbers. We will start with the classical computational requirements: storage, processing power, energy costs dictated by Landauer's principle. Those numbers are immense, but not necessarily fatal for a sufficiently advanced civilization. Then we will examine the empirical tests scientists have proposed: discretized space-time, rendering shortcuts, statistical fingerprints, and what experiments have actually found. And finally, we will reach the argument that no engineering can overcome: the quantum complexity barrier, a mathematical reality in which the resources required to classically simulate quantum physics grow exponentially with every single particle added to the system. This is not a matter of building a bigger computer. It is a fundamental limit on what computation can do. Let's see where the math leads.
This is the world that you know. The world as it was at the end of the 20th century. It exists now only as part of a neural interactive simulation that we call the Matrix. You've been living in a dream world, Neo. This is the world as it exists today.
Let's start with the logic trap. The simulation hypothesis says we might live inside a computer simulation created by some advanced civilization. It's the Matrix, but without leather and probably worse lighting. The modern, rigorous version of this idea was framed as a trilemma. Either one, almost all civilizations die before they can build ancestor simulations, or two, advanced civilizations have no interest in simulating ancestors, or three, we are almost certainly living in a simulation. If you reject one and two, you're pushed to accept three. Elegant, unsettling, and deliciously simple. But does simplicity equal truth? Not always. Before we judge, let's ask the right questions. What assumptions does the hypothesis rely on, and can those assumptions be tested? There are three big assumptions hiding behind the idea that we are simulated: computational feasibility, philosophical substrate independence, and the statistical argument about observers. I'll take each in turn and throw in a few numbers, because people in lab coats like things with digits. First, computational feasibility. Can a civilization actually simulate a universe, or even just a paste of life like Earth, with people and weather and coffee stains, without inventing magic? A lot of the drama collapses once you do some back-of-the-envelope math. The human brain is often the benchmark. If you can simulate a brain, you can simulate minds. A conservative neuroscience estimate gives us roughly 10 to the 11th neurons and about 10 to the 14th synapses for a human brain. If we store 1 byte per synapse, tiny, tight, and optimistic, that's 100,000 gigabytes, about 91 terabytes. That's one person's memory map at a synapse resolution level. Multiply by millions or billions of simulated people, and you're well into exabytes and beyond. If each synapse needed more complex state, milliseconds of potentials, ion channel states, detailed biochemistry, the cost skyrockets. But raw storage isn't the whole story. To run a brain, you need operations per second, synaptic updates, spike propagation, short-term plasticity. If each synapse updates on average 100 times per second, reasonable for many networks, then a single brain needs about 10 to the 16th operations per second. That's 10 petaflops of sustained computation per person. A lot, but not unattainable in principle for an industrial civilization with huge computational infrastructure. The kicker is scale. Simulating billions of brains, plus entire planetary environments at fine detail, is an astronomical, pun intended, computing problem. Now a reality check. There are physics-based limits on computation. Landauer's principle tells us there's a minimum thermodynamic energy cost to erase information, about 2.87 times 10 to the minus 21 joules per bit at room temperature. Sounds tiny, and it is tiny, but multiply that by the billions of bits you'd flip per second, and you get a real power bill. Still, thermodynamic limits are not showstoppers. They set bounds, not impossibilities. In short, computationally hard, may be expensive, but not obviously physically impossible. So an advanced civilization could plausibly have the hardware for simulations, if they want to build it. Second assumption, substrate independence of consciousness. This is more philosophical than physical. It supposes that consciousness can be implemented on any sufficiently complex computational substrate, silicon, biological wetware, whatever. If true, emulating the functional structure of a brain should produce the same conscious experience. If false, then even a perfect simulation of our atoms may not produce conscious beings. This is a tricky philosophical knot. There's no experimental proof either way. It's a metaphysical leap we often smuggle into these debates. We assume minds are software, not irreducibly tied to carbon wetware. Third assumption, the statistical argument, often called the simulation argument proper. The idea is simple. If A, advanced civilizations can run many ancestor-type simulations, and B, they do run a huge number of them, then the number of simulated conscious beings could vastly outnumber biological ones. by random sampling, you'd probably be in a simulation. That move converts computational plausibility into probabilistic inevitability. The great weakness is that it replaces one unknown with another. We don't know whether future sieves will run ancestor sims, and if they do, how many. Large numbers amplify uncertainty. They do not resolve it.
Okay, fun so far, but let's ask, can we test the idea scientifically? At first glance, no. A perfect simulation would be made to be indistinguishable from base reality, but the clever people don't stop there. Scientists and philosophers have proposed possible empirical signatures, subtle cracks that a simulated universe might reveal. I'll run through 3 main testable predictions that have been discussed in the literature and what they mean. Test 1. Discretization of space-time. If a simulation runs on finite resolution hardware, the simulated space might have a smallest unit, a lattice spacing, analogous to pixels. That could show up as violations of Lorentz invariance or energy momentum conservation at extreme energies. In the real world, we look for these signs in ultra-high energy cosmic rays and in the behavior of gamma rays. If particle energies show unexpected cutoffs or preferred directions aligning with a lattice, that could hint at an underlying grid. In practice, tests are hard and signals ambiguous. Physics experiments thus far show extremely tight Lorentz invariance, so this test has not yet revealed smoking guns. Test 2. Computation-Limited Anomalies. Rendering shortcuts. In complex graphics, video games don't render what you're not looking at. Could a simulator save resources by rendering detail only when observed? That idea predicts observer-dependent decoherence or improbable correlations at the edges of observability. In quantum mechanics, measurement already plays a weird role. Some have suggested that looking for observer-dependent collapse anomalies could offer clues. So far, quantum experiments remain well described by standard quantum theory, but quantum foundations are subtle and contested, not an obvious smoking gun, more like a philosophical eyebrow raise. Test 3. Statistical signatures in natural randomness. If the simulation uses pseudo-random number generators for large stochastic processes, certain statistical fingerprints might appear: non-ideal randomness, patterns, or repetitions. For instance, if very large-scale cosmological fluctuations or extreme events show unexpected regularity, that could be a hint. But natural processes and chaotic systems produce patterns too, and finding a pattern is not the same as finding a program. It's easy to mistake structure for intention. So the empirical roots exist, but all are difficult and ambiguous. Now some math to show the sort of reasoning scientists actually use when testing these ideas. Remember our earlier synapse numbers: 10 to the 14th synapses, roughly 91 terabytes at 1 byte per synapse. If we require, say, 100 updates per second across those synapses, that's roughly 10 to the 16th updates per second, roughly 10 petaflops. Multiply that by 1 million simulated people, tiny compared to Earth's population, and you need 10 to the 22nd operations per second. Those are monstrous numbers. The upshot: if the future civilization is running such sims, either they have unfathomable compute or they limit the simulation in clever ways: coarse-grained physics, selective fidelity, or partial realism. That gives us a clue. If simulations are being run, they're probably not perfect atom-for-atom recreations of entire planets. They're optimized. Which brings us to a powerful critique: Occam's razor. The simulation hypothesis often flips Occam on its head. Instead of positing a simple, elegant underlying reality, it posits a more complex infrastructure behind everything. Why not accept the simpler explanation that reality is real, unless there's good reason to posit a simulator? Proponents counter that the simplest statistical expectation given multiple ancestor simulation instances leads to the simulation being more likely, but that argument depends on debated priors. Bayesian inference is great, but garbage in yields garbage out. Another philosophical crack appears in the idea of ancestor simulations themselves. If the goal of these simulations is to study history,
they must be sufficiently accurate to produce the phenomena of interest. But many scientific phenomena are emergent and sensitive to tiny differences. If you fuzz out the microphysics to save compute, you might miss the very effects you'd want to study. So it's plausible that advanced simulators either simulate only what's needed, or they simulate at high fidelity but only for a tiny sample. Both options undermine the "we are almost certainly simulated" probability boost. Let's talk about falsifiability, because that's the heart of scientific respectability. A hypothesis that cannot be disconfirmed is not science, it's metaphysics. The simulation hypothesis can be made unfalsifiable by building simulators who intentionally erase evidence of their own existence inside the simulation. That's cheating. But if we restrict ourselves to the weaker claim that a simulation might leak detectable signatures, then it becomes at least partly testable. Look for Lorentz violations, search for anomalous cosmic ray cutoffs, examine statistical randomness in the cosmic microwave background, and scrutinize the quantum measurement problem. So far, no convincing leaks. Now for a thought experiment to sharpen intuitions. Imagine a future civilization that wants to study your neighborhood in detail. Not you personally, but social dynamics at the block level. It wants to run 1,000,000 Monte Carlo histories to understand how neighborhoods evolve. It will likely simplify, approximate molecules, simulate weather with fluid approximations, and model people as agents with compressed internal states. The simulation will be optimized for the questions the civilization cares about. That implies many simulations would be low fidelity in everyday details. You being conscious matters only if the simulation architecture preserves whatever substrate independence is required. That reduces the probability that your precise reality is a perfect, high-res copy. I promised jokes sprinkled in. Here's one. If we are in a simulation, at least the lag is not our fault. And if you see a frame drop, don't blame your ISP, blame the simulator's GPU. Back on the serious channel, let's discuss the astronomical number objection. A common reaction is, there could be 1 trillion simulated minds, so probability skyrockets. But quantifying that trillion requires assumptions about future demographics, values, and ethics. Will advanced civilizations simulate suffering? Will they have reasons to run ancestor simulations? They might consider it unethical. Or they might find simulations boring and prefer other research. These are empirical sociological questions about hypothetical civilizations, not physics. We can't reliably assign probabilities to them. What about consciousness as evidence? Some argue that subjective experience feels real, and that such realism indicates a base reality. But that's a philosophical move. Your experience doesn't give a meta-ontological certificate. If you're simulated, you'd still have vivid experiences. That's the creep. The simulation hypothesis is consistent with virtually any observation you make inside the simulation, which makes falsification tough. So what is the best scientific stance? Skeptical, curious, and cautious. Simulation theory is a serious philosophical and occasionally scientific conversation starter. It has motivated, clever empirical proposals, which is good. The correct scientific attitude is to test the testable and admit the limits of the rest. If future experiments found Lorentz violations implying a lattice scale, or if cosmic ray spectra showed telltale anisotropies tied to a grid, that would be revolutionary. Until then, the hypothesis sits in a gray zone, interesting enough to discuss, but not yet evidence-backed. Now, if you have been following closely, you have spotted the escape hatch in my quantum complexity argument, and you are right to reach for it. You proved that no classical computer can simulate quantum mechanics efficiently. But what about quantum computers? Feynman himself proposed quantum computation precisely because quantum systems simulate other quantum systems without exponential overhead. Give the simulator a quantum computer, and your scaling argument evaporates. This is the strongest counterargument available. It deserves a precise answer. and it gets 2. First, the resource problem does not disappear. It transforms. To quantum simulate a system of n particles, you need a quantum computer with at least n qubits, particles of physical matter maintained in coherent quantum states. To simulate our universe's roughly 10 to the power of 80 particles, you need a machine containing at least 10 to the power of 80 coherent qubits. That machine is itself a physical system, occupying space, consuming energy, obeying whatever thermodynamic laws govern the simulator's reality. It must be at least as large and complex as the universe it models. At that point, you haven't built a simulation, you have built another universe. The word simulation has become a label with no content. But the deeper wall is not physical, it is mathematical, and it applies to every computer that could ever exist, classical, quantum, or otherwise, under any conceivable laws of physics. In 1936, Alan Turing proved that no computational system can universally predict whether an arbitrary computation will finish or run forever. This is the halting problem, and it is not a technological limitation. It is a theorem, a proven, permanent boundary on what computation can determine about computation. Now apply this to simulation. Our universe contains computers, biological ones like human brains, and increasingly artificial ones. A faithful simulation must reproduce the outputs of those computers exactly. But Turing's proof tells us that some of those outputs are undecidable in advance. The simulator cannot shortcut them. It cannot predict what a computing being inside the simulation will calculate next without actually executing the full computation step by step in real time. Every abbreviation risks producing a simulated mathematician who proves false theorems, a simulated physicist whose experiments contradict the very laws the simulation is supposed to encode. And here, the problem recurses. If a civilization inside the simulation builds its own simulations, which we, right now, are already doing, the simulator must simulate the simulation. And if that inner simulation contains beings who build further simulations, each layer demands full computational fidelity for every layer beneath it. The cost does not merely grow, it nests, it compounds. And at every level, the halting problem guarantees that no layer can be compressed without risking logical contradiction. This is not about processing power or cleverness. It is about what computation itself can and cannot do. Turing didn't prove that today's computers can't solve this problem. He proved that no possible computation can. Not on silicon, not on qubits, not on substrates from a universe with laws we have never imagined. The proof is mathematical. It is substrate independent. It is permanent. So the simulation hypothesis now faces a trilemma of its own, one far less comfortable than Bostrom's. Either the simulation doesn't faithfully reproduce computation, in which case it isn't simulating minds, and consciousness is an illusion inside it, or it does reproduce computation faithfully, in which case it requires a machine at least as complex as reality, and the word simulation means nothing, or it tries to shortcut the computation, in which case Turing's theorem guarantees it will eventually produce a logical contradiction, a glitch not in the rendering but in the mathematics of the simulated universe itself. Pick your option. None of them lead to, we are probably simulated. Let's lay out what the evidence actually establishes. The classical computational requirements for simulating a universe are enormous. Exabytes of storage, 10 to the power of 22 operations per second, energy budgets governed by Landauer's principle, but not theoretically insurmountable for a sufficiently advanced civilization. That layer of the simulation argument, while strained, survives contact with physics. The empirical tests do not rescue it. No experiment has detected lattice-scale Lorentz violations. No cosmic ray spectrum reveals grid-aligned energy cutoffs. No structure in the cosmic microwave background betrays a pseudo-random number generator. Every measurement we have is consistent with a universe that is continuous, isotropic, and unsimulated. But it is the quantum complexity argument that closes the door and welds it shut. The Hilbert space required to describe a quantum system scales as 2 to the power of n, where n is the number of particles. For just 300 particles, that yields approximately 10 to the power of 90 dimensions, 10 billion times more than the total number of atoms in the observable universe. For the universe's actual 10 to the power of 80 particles, the dimensionality becomes 2 to the power of 10 to the power of 80, a number so vast that no notation in mathematics makes it feel small. This is not an engineering bottleneck awaiting better hardware. It is a scaling law, a boundary built into the structure of computation itself. No classical computer, not one constructed from every atom in every galaxy we can observe, could store the quantum state of a single gram of matter, let alone simulate its evolution forward in time. And here is the deepest consequence. The only system capable of computing the quantum behavior of the universe with perfect fidelity is the universe itself. Every entangled pair, every superposition, every quantum field interaction is a calculation executing in real time at a density of information processing that no external machine could replicate. Reality is not running on something. Reality is the computation. Any machine built to simulate it would need to be larger than the universe it attempts to model, at which point you are no longer describing a simulation. You are just describing another universe. What we are part of is not a program. It is a self-computing quantum system whose full description exceeds the capacity of any computer that could ever be constructed within it. That is not less remarkable than being a simulation. It is incomparably more so. Now, every claim I have made in this video is mathematically specific and, in principle, falsifiable. If you can resolve the exponential scaling problem, I want to see your argument. I have opened the Community tab for exactly this purpose. Post your calculations, share published papers, challenge the numbers directly. Science does not advance through agreement. It advances through rigorous attempts at demolition that fail. Subscribe to the Cosmic Codex for more arguments built on evidence rather than assumption. And the next time someone tells you we are living in a simulation, ask them one question. How do you plan to classically simulate a Hilbert space of dimension 2 to the power of 10 to the power of 80? Then watch them change the subject. Until next time, demand the math.